In Chapter 10, we compared the mean response for two levels of a categorical variable, and we could do that whether we had independent or dependent samples. Now we're going to extend that a little bit in Chapter 14 using something called ANOVA. And we've seen ANOVA when we did regression, and now we're going to look at it when we have a categorical predictor. So we're going to start off with the beer goggles example. And these data, the beer goggles data, are available on ELC. So the question is, a psychologist, we'll phrase it this way. A psychologist designed an experiment to study the effect of alcohol consumption on people's perception of attractiveness in others. So these aren't the beer goggles that you might put on in a health class to see that the more beer that you drink, the blurrier your vision gets. It's about the more beer you drink, the better looking people tend to be, or tend to appear. In this study, participants were randomly assigned to drink 0, 2, or 4 pints of a strong lager, and they were set free to chat up potential mates in a nightclub. At the end of the study, the photos of the people the participants talked to were taken and rated for attractiveness by independent raters, and this was done on a 0 to 100 scale. So our explanatory variable in this case is the amount of beer. And in this case, this is actually a categorical variable. If you were to take a more advanced statistics class, like a design of experiments class or a more general linear models class, we could see how we could treat a categorical variable like this, which could also be seen as levels taken from a quantitative variable. We could do some more interesting analyses, but this really is categorical. We're assigning people to one of three groups, the 0, 2, or 4 pints group. And the response variable is quantitative. That is the amount of attractiveness or the level of attractiveness. So please note that it is not the people who drank that are rating the conversation partners for attractiveness. The assumption here is that we're only going to talk to people that we find attractive in some way. And so we need independent raters to rate the participants' conversation partners. So if we wanted to do a two-sample t-test on these data, what would we have to do to the explanatory variable? Because here we've got 0, 2, or 4 pints. We've got 3 levels of the predictor. We've got 3 samples, a 0 group, a 2 group, and a 4 group. So if we wanted to run a two-sample t-test, we would have to make it binary. Perhaps beer versus no beer. So we would have to group perhaps the 2 and 4 pints group into one and compare that to the 0 pints group. Because a two-sample t-test requires 2 samples. If we had more than 2 samples, we would have to run multiple tests. And if we did that, it would increase our risk for type 1 error. So let's consider this further. So how could we compare these 3 groups, the 0, 2, and 4 pint group, and the attractiveness of the people talked to by people who consume this amount of alcohol using just one test, so without having to make this binary? We can do this using analysis of variance, or ANOVA. The analysis of variance is a test, or more broadly a model, of the null hypothesis of equal population means, or that the mean of the response is the same for all levels of the explanatory variable or the predictor. So for this example, our null hypothesis is that mu 0 pints equals the mean attractiveness for people who drink 2 pints is the mean attractiveness of the people talked to by those who drank 4 pints. The alternative, like we saw with multiple regression, is at least one mean differs. That all of the means are not the same, that at least one of those means is different from the rest. And of course we define our parameters in context. So where mu j is the true mean attractiveness of the conversation partners for participants who drank 0, 2, or 4 pints of lager, respectively. So the people who drank 0 pints of lager, they drank some amount, they talked to people with some true average attractiveness. The people who drink 2 pints of lager, they tend to talk to people with some amount of attractiveness. And the people who drink a lot of beer, 4 pints, tend to drink some amount of attractiveness. Now, if we really think that there is a such beer goggles effect, this null hypothesis is garbage, right? We don't really actually believe that the null hypothesis is true, right? So we have to keep this in mind, that there's no way that we actually believe that this is true. But we're starting somewhere, that there is some effect. So let's consider some possibilities. This is what is at the heart of any analysis of variance. And we asked a similar question when we looked at 4 regression plots back in chapter 12. So which of these data sets represents the strongest evidence against the null hypothesis? So we've got plot A, we've got plot B, plot C, and plot D. So which of these represents the strongest evidence against the null? So the strongest evidence that at least one population mean differs. So these are sample data. Which of these 4 plots represents the weakest evidence against the null hypothesis? The weakest evidence that at least one mean differs. So we can see in plot A that the mean of the 4 pint group is actually lower than the means of the 0 and 2 pint group. But there's a lot of variability, a lot of spread in these groups, so they're not very distinct. The means of the groups in plot B, they're the same as in plot A, but there's less variability, so they seem more distinct. Now in plot C, the means are less different. So the means for the 3 groups are less spread out. And the means in plot D are the same as the means in plot C, but we can see that there is more variability. And so if we use the idea of explained and unexplained variability, the differences between the groups in plot B are very big. I can explain why the mean for the 0 group, the 2 group, and the 4 group are different by the amount of beer. So there is large explained variability. Differences between groups. And there's relatively small unexplained variability. I can't explain why everyone who drank 4 pints didn't talk to people of the same attractiveness, but there aren't that many differences. Similar to people who drank only 2 pints of beer, I can't explain why they didn't all talk to people of the same attractiveness, but the differences for people who drank 2 pints of beer are relatively small. So there's relatively small unexplained variability. That would be differences within the groups. So group B has the strongest evidence because the groups are the most distinct. The differences between the groups are the largest, and the variability within the groups, the unexplained variability, is the smallest. Whereas group D, or plot D, has the weakest evidence because the opposite relationships hold true. The variability between the groups is the smallest, and the variability within the groups is the largest. So how do we formalize that? We can use the ANOVA F-statistic to compare the means, and that has the F sampling distribution when the null hypothesis is true. So F, or F-obs, is our between groups variability, divided by our within groups variability. just like we saw with regression, that is our explained variability divided by our unexplained variability. The degrees of freedom for my F statistic are just like what we saw with the ANOVA for regression as well. My degrees of freedom, 1, my numerator degrees of freedom, is the number of groups minus 1. Well, the number of groups is the number of means that I'm estimating, and that's the number of parameters minus 1. My degrees of freedom for the denominator are my error degrees of freedom. Well, that's going to be n minus the number of groups. But like we just said, the number of groups is the number of means that I'm estimating. So that's going to be n minus the number of parameters. So we'll call this my degrees of freedom for the model, or between, and this will be my degrees of freedom for within, or error. So if my null hypothesis is true, this is going to follow the F distribution, and there can be a lot of different F statistics. And if I have a lot of between groups variability and very little within groups variability, then I'm going to end up with an F statistic way out here. And that's unusual. And my p-value will be everything greater than that. And that's evidence against the null hypothesis. So to make this ANOVA valid, I have to come up with some assumptions. So first, should be pretty familiar, because we're always checking for approximate normality when we have a quantitative response. So my response should be approximately normal for each of those G populations. So for every level of my predictor, the response should be approximately normal. And the F is robust to small departures from normality. So if I have some slight skewness, I should be okay. I check this by looking at a histogram of the response in each group. The second one is just like we saw in regression. Is the standard deviation of the response the same for each level of the predictor? So do I have the same standard deviation for each of the G population distributions? So I check this. Instead of looking at a residual plot, I just find the standard deviation for each of the groups, and I find the largest standard deviation, we'll call that S max, and I find the smallest group standard deviation, and S min. And as long as S max over S min, the largest standard deviation over the smallest, is less than 2, then I'm okay. So that's also saying, is the largest group standard deviation less than 2 times the smallest group standard deviation? Because if it is, then that means the 2 standard deviations are similar enough that any other comparison that I make means that all my standard deviations are relatively close to each other. I also have to check that I have G independent random samples. So to do the 2-sample t-test, I had to have independent random samples, and now I'm just comparing more of them, so I still have to have independent random samples. So I can do this either by random assignment, if I do an experiment, and this has the added benefit of getting cause and effect relationships. But if I'm doing an observational study, I need to do random sampling from each of the G populations. And this would be like if instead of looking at the mean of just plain and peanut M&Ms, we were also looking at plain, peanut, dark chocolate, pretzel, crispy, and so on. And we'd have to take a random sample from each of those distinct types of populations. And that would be for an observational study. We wouldn't be able to look at cause and effect relationships, but I could still have independent random samples, and my F-test for this ANOVA would still be valid. And then finally, I just have to make sure that I have the right kinds of variables to begin with. So do I have a quantitative response and a categorical explanatory variable? So let's look at an example. Does a picture have any effect on the college student's understanding of ambiguous prose? So students were randomly assigned to one of three groups. One saw a picture before hearing a difficult passage of text, one saw the picture after hearing the passage, and the third group was not shown a picture at all. Each of the three groups were then tested on their comprehension of that passage that they heard. So we have three levels, so this is a categorical predictor with three levels when they heard when they saw the picture, if they saw it at all. We have an equal number of students in each group, and we have the mean response and the standard error of the mean in each group. We have our F ratio and the probability that we're greater than F, so this is our p-value. So, a few things. Let's check our assumptions. Is the normal distribution reasonable? In this case, we have slight skew. So here we have a slight right skew for the group that did not see a picture. Here we have a slight left skew. And again, for the group that saw the picture after hearing the passage, there is slight right skew. But we remember that the F-test is robust, so we are okay. If this were much more heavily skewed, we'd be concerned. We have similar sample sizes. So that's also supportive of this F-test. We have similar sample standard deviations. So this should be standard deviation, not standard error. So none of those. So our largest standard deviation is 1.39. Our smallest standard deviation is 1.26. That ratio is less than 2. So we have roughly equal standard deviations in our sample, so the F-test is okay. For random assignment, we have achieved that. We are told students were randomly assigned to one of three groups. So that means we also have independent samples. Because of this random assignment, our conclusions can be about cause and effect. We have a quantitative response. That's their score on their comprehension. And we have a categorical predictor, which is the group they were in, the after, the before, or the no seeing picture group. So, what is our hypothesis? The null hypothesis is that the mean comprehension for the before group is the same as the mean comprehension for the after group, is the same as the mean comprehension for the not seeing a picture at all group. The alternative hypothesis is that when you see the picture makes a difference in terms of the comprehension, so that at least one of these means differs. And we're of course going to define our means. So mu j is the true mean comprehension of ambiguous passage for students who see the picture before, after a passage, or don't see one at all. Now, let's think of our results. Our F statistic is 10.02. So our F-obs is 10. That means we have 10 times as much explained variability as unexplained variability. And that's a pretty large effect, especially given that we only have 19 observations per sample. Our p-value, also provided, is 0.0002. So if exposure to the picture, whether before or after or not at all, makes no difference on the average contribution, then we would see an F statistic at least this large 2/100% of the time. We would see this kind of statistic very rarely. So remember, we're dealing with something way out here. We have a tiny little p-value if the null is true. Very unusual. So we have a large effect, we have a reasonable sample size, and we have a very small p-value. Our data are highly compatible. We have very strong evidence against that null hypothesis. Our data are highly compatible with the alternative that at least one mean differs.